Hello everyone and welcome to this webinar. My name is Olivier Arnaud. I am an application engineer in the Mentor PCB division, but I happen to be a former IC designer, so I am familiar with the kind of problems we'll describe during this session. Before we start, I must warn you, although I'm pretty sure you've already figured it out. I'm afraid I'm French, so do not expect a Cambridge accent during this session. Hopefully, it won't be a problem, and anyway, I know that the product demonstration will speak by itself. A demo is worth 1,000 words, with or without a French accent. So the topic of this session is FPGA onboard integration, and the solution Mentor provides to make you save a lot of time and money. Ioptimizer is one piece of the unique Mentor PCB design and verification integrated flow, and more particularly the design optimization process. It entirely relies on the best-in-class tools that Mentor owns, making a full integration within the PCB design flow possible. In many companies, FPGAs and boards are developed by two separate teams, sometimes located in different places, countries, or even continents. So it is very frequent that FPGAs and the board which will receive them are designed in isolation, using the traditional over-the-wall methodology consisting of exchanging files in a very informal way. The experience shows that this is a perfect recipe for a disaster. With multi-thousand pin devices, and without the appropriate design methodology based on an efficient I optimization, but also on an optimal FPGA onboard placement, FPGA onboard integration may lead to unroutable boards, which require best case several time-consuming iterations between the FPGA and the PCB design teams, and worst case a change of the board size or board stack-up, inducing unexpected extra costs. The methodology enforced by Ioptimizer minimizes the risk that the best case and worst case scenarios described above occur, first by enabling an efficient and formal collaboration between the design teams, and second by providing the technology to concurrently optimize both FPGA placement and I/O optimization. All major FPGA vendors are supported: Intel FPGA, formerly Altera, Xilinx, Microsemi, and Lattice. Libraries are updated regularly and can be live updated from within the application. Missing models can be developed very quickly on demand at no extra cost for customers on maintenance, with an average delivery time of 2 weeks, depending on the device complexity. It is not rare that we work with the FPGA vendors to develop and deliver to our customers early models for pre-release and restricted devices so that they can work on their next board generation with no delay to decrease their time to market. Let's now move to the product demonstration. The project we will use today is made of two FPGAs connected together and connected to the outside world via two connectors. The first FPGA is called controller and was created earlier. It was instantiated on two sheets in the schematic. One sheet for the functional pins already connected to the connector with the reference designator PL2. The other sheets for the power, ground, and configuration pins. Notice that these symbols are not connected yet. So there is no hierarchy involved, but a flat approach has been adopted for this FPGA. Looking at the controller symbol property, we can see that it is of a type FPGA, reference designator is U1, and package group is FPGA A1. The controller FPGA has been already packaged and placed in the layout. You can see in the layout editor the net lines between the FPGA and the connectors. Notice that some traces from the connector are partially routed. For the second FPGA called image processor, we'll take a different approach as we'll use a hierarchical functional symbol to expose the functional pins. All the FPGA symbols will be placed on two sheets in the lower level underneath, one sheet for the banks and one sheet for the config, power and ground symbols. Very similar to what we did for the first FPGA, but this time we've introduced hierarchy. This FPGA is connected to another connector with reference designators PL1. We will create the second FPGA from scratch and instantiate it once done. The creation of a PCB part for a big FPGA device with a few thousand pins is extremely time-consuming and error-prone. Before the part is ready to be used in a design, it can easily take a few days. The FPGA part wizard is a utility available in library tools to create such a part in minutes. It gives you access to the main FPGA vendors' device libraries, Intel, Altera, Xilinx, Microsemi, and Lattice. You can directly select the device you want if you have this information, or use the filter to help you out. The image processor FPGA will be a device of the Xilinx Vertex 4 family. The package will be a FPGA with over 1000 pins, 1148 pins to be precise. The right pane of the FPGA part wizard always shows users a preview of the symbols reflecting the different options they choose. The show border feature is very useful to get a good idea of the size of the symbols which will be automatically created. You can then eventually split the big ones to fit your standard sheet size. It is usually a good idea to check the power symbol, which is often the biggest. The D sheet looks like a good choice here. You then flip to the different pages of the wizard to specify the options you prefer. The right pane is dynamically changed to reflect your choices. You can enforce a symbol prefix to differentiate symbols in the library. The symbol name is changed dynamically. You can decide how you want the symbol to be split. By banks is a very common and judicious choice. You can optionally generate a separate symbol for JTAG, power, ground, and configuration. Various pin sorting options are available. You can customize the symbols created automatically in the custom area, where you can move pins between symbols, merge symbols, and so on and so forth. Some symbols and pin properties can be predefined upfront in the project settings. They would appear here. The symbol appearance can be modified. You have a few options to define how to label the pins. Pin function is a very common one, and additional labels. Position and alignment options can also be changed according to your own rules. More graphical settings are available to better control the readability of the symbol. You can control, for example, the pin spacing, the pin length, the size of any text used in a symbol, and so on. Then you choose the library partition to store the symbols and the part that will be created. You need a part number, which is the unique identifier in the library. A name is suggested by the wizard. You can modify it. Part name and label can also be entered. The wizard only offers the footprint of the library with the correct number of pins. Note that you can also enter a new name if you plan to create the footprint later. And you're ready to export to the central library. In a few seconds, you're done. The symbol have been created and associated to the footprint to create the part. Ready for instantiation. We can check in the partitions we chose earlier that symbols and part have been created in the right location. Back to our schematic, the project integration dialog indicates that the library has been updated. You click on the Amber button to update your design environment. We're now ready to instantiate the newly created symbols. This can be done from the search window in the Library Parts tab, where you can select the FPGA part type. Our Vertex 4 device is available and the symbols can be placed via the dedicated Place FPGA command. We place the bank symbols on the first sheet and the other symbols on the second sheet. Using this place command from the search window eliminates the risk that you instantiate the same symbol twice and that you forget to instantiate one symbol, which can happen when you have a few dozen symbols for one part. The show alignment markers features of the schematic editor happens to be pretty useful while placing FPGA symbols. The special field FPGA area, which allows easily identifying the FPGAs in the schematic, is a display option. It can be disabled if needed. You can abort the command and restart it. The next unplaced symbol will be available on your cursor. Once everything has been placed, we can now bring up Ioptimizer or Iopt to create one Iopt database per FPGA to start working on the IO assignment. You select one of the FPGA symbol and invoke Iopt through the FPGA HDL optimize FPGA command on the right mouse button. A wizard will show up. The two first pages are informational as the FPGA was created earlier in the library. In order to read the port information of the image processor FPGA, we'll use the VHDL file we got from the guy in charge of designing the FPGA. Note that we actually parse the VHDL and would report an error if needed. We go to the remaining informational wizard pages and push the Finish button. The VHDL ports have been extracted and will be added to the database. The pin direction comes from the VHDL file too. You can then change the I/O characteristics if needed. You can also read an FPGA constraint file if available to set this up automatically. This is more likely what you would do. The pin haven't been assigned yet, so this is the next step, your next step. We'll simply assign all input pins on the left side of the device and all output pins on the right side. Note that by pressing the Control key, you can place the pin vertically. With the Alt key, you can fit the pins in the same bank. There are various techniques available to ease this phase. It is always a good idea to check that all pins have been assigned. So we're all good. Let's now create one Iopt database for the second FPGA. It can be done in the same Iopt session. This time we do not need a VHDL file to read the port information, but instead we will extract the same information directly from the schematic. And this time the pins are assigned, as we saw earlier on the schematic. For this FPGA too. We can now back annotate the schematic with the newly entered information. This step is particularly interesting as it also connects the power and ground pins automatically according to the user's defined settings. During this phase, you can also optionally generate a functional symbol for your FPGA. We won't do it as the functional symbol already exists in our schematic or is not needed. Control FPGA is flat. Back to the schematic, the project integration dialog indicates that some FPGA Iopt information should be back annotated to the schematic. A simple click will update the schematic for both FPGAs. We can see that the power and ground pins have been connected, as well as some functional pins. The schematic being in sync with Iopt, we can now forward annotate the changes to the layout tool. So we bring up the project integration dialog and push the amber button. Once done, the image processor FPGA will be available, ready to be placed in the layout. The net lines between both FPGAs and connectors are shown. We can save the updated layout. Back to Iopt, we will now optimize the I/O assignment based on the layout information. First thing, you don't want to see all components in your floor plan view, but only the relevant ones. You can filter them out easily through a simple regular expression. The latest layout information is loaded, but you can modify the placement, flip or rotate the FPGAs to minimize the number of crossovers. You can then start the interesting job of unraveling the selected netlines by swapping pins on the FPGA. The goal is to minimize the net crossovers, leading to shorter net length and less via. Notice that the partially routed nets shown earlier do appear in the floor plan view. Okay, so the result is okay but not great. So let's go back to the Iopt database and allow more swaps between, for example, between partitions for both FPGAs. It is important to understand that FPGA rules are systematically enforced by Iopt. So it will not swap a power pin and an IO pin, for example, or two pins with different power supplies. Iopt swaps are correct by construction. Let's allow more swaps for both FPGAs. So you save both databases and you update the floor plan view with the latest FPGA information. You can then rerun the automatic optimization and see the impact. It looks much better. You can update each FPGA individually or all FPGA at a time. It may take a bit more time, but it's likely to give better results. You can give Iopt even more flexibility by allowing the swap with the unused pins. Otherwise, it will try to swap assigned pins only. Once you're happy with the results, you can back annotate the schematic as shown previously. You can see dynamically how the schematic is updated. Back to Iopt, you'd like to preserve the placement you used to optimize the FPGAs. You do so by exporting the current placement. You can then update the layout database with the latest connectivity information and eventually apply the I/O placement. First, the connectivity, so the net lines will be impacted. Then the placement, which reflects what you have in the floor plan view. So let's quickly route a few nets with the sketch router to get an idea of what the routing can look like. Last but not least, you must send the new pinout information to the FPGA designers who need to check that the timings are still met before they can physically implement the FPGAs. Remember that in order to facilitate the routing of the board, you've swapped pins which may have modified the timing of the FPGA themselves. The FPGA designer must now verify that, for example, no race conditions have been introduced. Note that the HDL and constraints files can be part of the FPGA database, and any change which may impact the pin assignment will be flagged. It allows to formalize an iterative optimization process between the FPGA design and the FPGA design teams. The Xilinx XDC file has been generated reflecting the optimization performed in Iopt, ready to be read by the FPGA designer.